Hey guys, in this video we're going to look at 3.8 exponential growth and decay. This is just an area where derivatives come up in nature a lot. Alright, so let's start out. So if you have a function, I've got y of t here, t being time usually, which tells you a population size at a time t. Y grows exponentially if f grows at a rate proportional to its size. So that is, it's growing specifically this term here at a rate proportional to its size. So here is the rate, y is its size at any point t, at any time t, and the k tells us that it's proportional to its size. So the rate it's growing is proportional to its size. Now what that means, or I guess maybe intuitively, you can think of that easily enough. The more, let's go with bunnies. If you think of bunnies, the more bunnies there are, the faster their population is going to grow, because there's more bunnies to make more bunnies. So that tells you that it's going to be growing exponentially. Now, just a side note, this is what we call a differential equation. Rather, this guy is, because it's an equation that involves not only the derivative of y, but it involves y itself. And so anytime that happens, it's a differential equation. Because keep in mind, the independent variable here is not y. Y is a function of the independent variable t. Alright, so if this is our differential equation, it turns out the only solution for a differential equation like that is an exponential function. So that tells us that anytime we have this situation, that y must be some kind of exponential function. And in general, we can write it like this. Y is some initial value of y, so that's y of 0, wherever that population started, times then the exponential function e to the kt. So if you want to verify that, you can take the derivative of both sides. So on the left side, that's just dy dt. And on the right side, if I take the derivative, let me clean this up a little bit. If I take the derivative of the right side, keep in mind y of 0 is just a constant. So as a constant multiple, he's just going to come along. That's some initial value of y, some initial population. But now we want to take the derivative of e to the kt, again, k being a constant. So that is going to be e to the kt, but that is times the derivative of kt. So this is just the chain rule here. E to the kt times the derivative of kt. Well, keeping in mind that t is what we're taking the derivative in terms of, so that means we're just left with k. So what I'm interested in, does this look like ky? Well, it kind of does. So dy dt, if you put the constants together and then leave e to the kt out here, go back. I'll get rid of some of this. So if you put the k on the other side, let me move this stuff over and move that k to the far left, notice what you have here is k times, and this was what a y originally was, y of t. So we do have the original differential equation that we were expecting. Okay, let's look at this example here. At the beginning of an experiment, there were 2 protozoa. After 3 days, there were 22 protozoa. Assuming population exponential growth in this population, estimate after 6 days. So what we know is that there were 2 at the beginning, and what that does is that gives us our y of 0. Y of 0 is 2. All right. Then after 3 days, so now we know y of 3 equals 22. But before I write that, what we've got is that the equation tells us this should be e to the kt. But of course t in this case is 3. All right, so what that tells us, and we know that that is 22. So what that lets us do is figure out what k is, because we know, of course, y of 0, we just said was 2. So let me rewrite this here. We have that 2e to the 3k equals 22. Now I might divide on both sides and say now e to the 3k equals 11. Now the problem is k is trapped up here in the exponent, but easy enough to get rid of that. We can natural log both sides. Using our log rules, bring 3k down. Alright, so we have 3k ln e equals ln of 11. Of course, ln e is just 1, so that's going to go away, and that'll let us solve for k. K will be ln of 11 over 3. Alright, so that was just an example. We didn't use any calculus. That was just algebra, just to maybe not introduce, but maybe refamiliarize ourselves with solving these exponential functions. Okay, so let's get into an example where calculus is used. Strontium-90 has a half-life of 28 years. A sample has a mass of 50 milligrams initially. So first we want to find the formula for the mass remaining after t years. So knowing that it's got a half-life of 28 years tells us that y of 0, let me start here, y of 0, our initial amount is 50 milligrams, and we know that y of 28 must be 25. Because it took that long for half of that strontium-90 to, I don't know what you say, disintegrate? Chemistry is not my strong point. Okay, but we know also that this must have been given by a formula e to the k times 28. So let's figure out what k is, and then we'll have our formula for figuring out the population. All right, so we know that y0, of course, is 50. We've got 50 e to the 28k equals 25. And of course, solving that, or rather moving that 50 over to the other side, gets us 1/2. And then using our natural log trick, that's going to leave us with, so again, I'm just going to take this down, and ln of e will be 1, so I'm left with 28k equals natural log of 1/2. But of course, you can use some more log rules to say that this is the same as natural log of a negative natural log of 2. double check me on that. And of course, now we can just divide by k. So k equals negative natural log of 2 over 28. All right, so that tells us that y of t, the answer to number 1 here, y of t is 50, or y0, times e to the kt, but k being negative natural log of 2 over 28 times t. All right, now it's asking us to find the mass after 40 years. Well, easy enough. Just plug in 40. 50 times e to the negative natural log 2 over 28. 40 looks like that's going to come to about 18.57. And I assume we can't have fractions of strontium 90, so I'm going to round that up to 19. All right, so let's look at number 3. How long will it take until only 2 milligrams remain? Well, here we want to solve for t. Y value, though, is going to be my 2 milligrams. So I'm going to take 2, set that equal to my function, and then solve for t. Y equals e to the negative ln 2 over 28 times t, and we got to solve for t. So first things first, I can divide both sides by 50, and that gives me, switch to decimals here, 0.04 e to the negative natural log of 2 over 28 t. And now at this point I can natural log both sides to get my exponent out of the exponent. So I'll have natural log 0.04 equals negative natural log of 2 over 28 times t. And now I'll just divide both sides by that constant in front of t. So you've got 28 natural log 0.04 all over negative natural log of 2, which comes to about 130 years. All right. So notice these examples didn't use any calculus. The main idea is that these were using the differential equation idea that we looked at the beginning. So this is really just an introduction to differential equations. The book goes through a couple examples on Newton's law of cooling and interest rate, continuously compounded interest. So take a look at those examples, try some of the problems out of this section. I didn't assign very many, but give them a shot and let me know if you have any questions.